Okay, we do have two people who joined in, Eduardo and Joseph, so that's good. We left off the last time. Where? Let me see. We left off right about here, talking about the voltage maximas and minimas on the Smith chart and how they correspond to the point P min and P max. And P min and P max are where the standing wave ratio circle intersects the x-axis on the right side and where it intersects on the left side. Okay. Feel free. Yes, I will allow it. All right. So we've got P min and P max. And so basically the steps here, just to remind you, step one, always get the normalized load impedance. You got to divide by the characteristic impedance to get the normalized load impedance. You go to the Smith chart. You try to plot that on here. We're going to get some practice doing that. Once you do that, you get a dot on here somewhere like there. You draw a circle. The circle centered at the center of the Smith chart. It has to go through that point. Okay. So you draw your circle. You draw a line from the center of the Smith chart through that point to the outside. And what we're saying now is we are able to figure out how far away you are from a voltage maximum or voltage minimum by going from A to there. That would be a voltage maximum. The distance to get from A to P max is whatever that is. To get the P min, you'd have to come over here. This blue circle represents different locations on the transmission line. You can't just so you're at the load here, right? That's our ZL point. You can't just move anywhere on the Smith chart. Movement down the transmission line, if this is the load and you're moving toward the generator, that it's fuzzy, but it says toward the generator is this way. So it's clockwise. So you go clockwise from here. This is moving down the transmission line toward the generator. So at ZL, you are there. As you start moving back this way, it's equivalent to moving around this circle, okay? So if we want to get to the voltage maximum point, we got to get to P max. We are stuck to traveling on the standing wave ratio circle. We got to get from A to P max. To get the starting point, we draw the line all the way out through. We read the value off the outside scale. That's the one that's the wavelengths toward the generator. Our ending point is the P max point. If you looked at that, if you look at that point on your Smith charts, you'll see it's 0.25 wavelengths. So your ending point to get the P max is 0.25 wavelengths. Your starting point is wherever this line crosses the wavelengths of the generator scale. You subtract them, that's that. After you get that number, how would you get that number? The distance to P min. Add how much? Is it 0.5? Quarter. How far is all the way around the Smith chart? Exactly. So that's a common thing, right? Because you think, oh, one way around, it'll be one wavelength, but no, it's half a wavelength. So you go halfway around, which is a quarter of a wavelength. Think back to your formula for D max and D min. D min was D max plus lambda divided by 4. It's plus a quarter of a wavelength, or minus, but okay. So that's that. We're going to do a practice where we actually get to do one of these. So, okay, so that's that. Just the last thing I mentioned at the end of last time, I think, was your B max point corresponds to your I min. So in other words, if I asked what is the distance to the voltage maximum, and you calculated that, if I instead had asked what's the distance to a current minimum, it'd be the same thing. Okay. All right, so that's that. We get the standing wave ratio simply from the same point, wherever the circle crosses the x-axis. Okay, that's how you get the standing wave ratio. And so here's the D max and D min. So D min is just D max plus 0.25 wavelengths. All right. Okay. We've been working with impedances, but what about admittances? Well, admittance is just 1 over impedance, right? So we just do 1 over Z. All right. So 1 over Z, that's just 1 over this thing, right? And then you could, if you wanted to, you could multiply by the complex conjugate, top and bottom, right? And then you get, it'd be R minus JX. And then you'd get this times R minus JX, and you end up with that. That's great. That's if you wanted to actually calculate it by hand, but we're going to do it on the Smith chart. And luckily, super easy to do on the Smith chart. Okay, so how do you do it? Well, first of all, you know how we deal with the little ZLs? Well, we're going to deal with little YLs. And in general, little y's. In other words, we have to normalize it. So you know how we normalize all of the little z's by dividing by z naught? We normalize all the y's by dividing by y naught. Where y naught's just 1 over z naught. So if z naught's 50, it's just 1 over 50. So we just divide everything by that, okay? So I just said it was really simple, and this isn't going to make it look simple. But basically what we got here is to get the little y, you got to divide it by the y naught, which is just 1 over z naught, right? So that's actually the same as multiplying it by, so this is 1 over 50, right? If z naught's 50. So that like brings the 50 up, right? So that's the same as 1 over little z. And then you could break it into a real part and an imaginary part. And really what we're going to do here is something really simple that this line shows the math behind it. And basically what this line says is one way that you could, one formula for ZL is 1 plus gamma over 1 minus gamma. It's not the one that I normally remember. Me personally, I remember gamma as ZL minus Z naught over ZL plus Z naught. And then if I really wanted to, I could rearrange that equation to solve for ZL. And that would be the unnormalized ZL. And if I wanted the little ZL, I could just divide by Z naught, okay? But basically that thing is equivalent to this. And you know, that ZL is just this over that because this is flipped, right? Well, if you said, well, what's my Z, but at a location a quarter wavelength away? If you did that, the reflection coefficient gets a phase shift of pi, which flips the signs, okay? This flips the signs, which makes it equal to this, right? Like these are equal to each other. Oh, I messed that up. Those are equal to each other. What that means is YL is equal to your impedance a distance quarter wavelength away. So what does that mean on the Smith chart? It's a lot easier than that equation is. It's the opposite side. It's 180 degrees away. Because remember, a quarter wavelength is halfway around the Smith chart. So let's say this was your load impedance. You do your usual thing. You plot it on there. You draw your line up through. You draw your circle. If you want the load admittance, you just extend this line all the way backwards through. So it's one line that completely goes through the Smith chart. Now this line has to go through the center. It's got to go through your load impedance. Wherever it crosses on the opposite side, it's 180 degrees away, or lambda divided by 4, right? Because it's halfway around the Smith chart. Wherever it crosses on the opposite side, that is your admittance. Okay, we're going to do a practice one of these. Okay, so for the next while, we're just going to do this example. We're going to kind of use everything that we've learned about the Smith chart so far. We're going to do the reflection coefficient, standing wave ratio, distance to the first voltage maximum, first voltage minimum, input impedance, input admittance. It's kind of everything that we've done. We're going to take our time with this. I'm going to give you a little bit of time to actually do it yourself. So if you don't have a Smith chart, let me know. Okay. Because you definitely want to try this. You don't want to just sit back and kind of watch. All right. A 50 ohm lossless transmission line of length 3.3 lambda is terminated by a load impedance ZL equals 25 plus J 50 ohms. Use the Smith chart to find a bunch of stuff. All right. Where should we begin? Yeah, we got to normalize. We can't do anything on the Smith chart unless we normalize. We get our little ZL, which is big ZL divided by Z naught. ZL is given to us as 25 plus J50. We got to divide that by Z naught. What's Z naught? 50. That's what tells you Z naught equals 50. We use 50 a lot, but don't always just assume it's 50 because it could be something different. So we do that, and that 0.5 plus J, I'll put a 1 there, but you don't have to. All right, so if you read this initially, you might not like that very much. You might be like, ugh, I don't know what that means, or I'm not sure how that's going to play into things. We'll worry about that later. Other than that, though, we're kind of ready to go here. We got our point there. So now it's time to go to the Smith chart. So we'll pop over to the Smith chart. Here we go. I'm going to write down my ZL. And now it's time to plot that dot. I'm going to let each of you try to find the spot. I'm not going to say anything. I want you to think about it. I want you to maybe struggle with it a bit. I'm going to give you a couple minutes. If it's easy for you and you get it right away, then carry on to trying to figure out the reflection coefficient. Yeah. There you go. What's that? It is a 1. Yep. Okay. So what is your first thought? You're looking at this ugly thing. It's got all these circles and lines and curves and arcs, and you've got a number, you know it's got to be 0. What is it? 0.5 plus J1? 0.5 plus J1. So what's in your head when you start this thing? Where's your head at? 0.5 where though? So you're talking about that? Okay, so you want to be at 0.5 on that? That's where we're looking. Now, just remember though, that 0.5 corresponds to everywhere. Okay. Okay. So that's how you do it. Real part first. To find the real part, look at these numbers across the middle. Those numbers across the middle correspond to not a single point here, but an entire circle. In other words, that alone does not tell you where the load is. You have to have that together with the imaginary part. How do you find the imaginary part? What makes you think that? Exactly. So the real part is always a positive number because it represents essentially a resistance. The imaginary part can be positive or negative. If it's positive, you are in the upper half of the Smith chart. If it's negative, you are in the lower half. Okay. Okay. So where am I going to look for the numbers? I'm going to zoom into the top half because that's what I'm interested in. I've eliminated the bottom half. Okay, and where am I looking for this number? Like, there's so many numbers on here. Okay, so I really want to look at these numbers along the outer edge. Okay, there's other places where the numbers are as well. For instance, down here, but that's good. Okay, so I want to look for the 1. And 1 corresponds to that entire arc. The 0.5 corresponds to this entire circle. So it's the intersection of those two that is our ZL point. All right, any questions about that? To get the 0.5 plus J1 was from just dividing the ZL by Z0. Yeah, okay. And sometimes you might be given that directly, and sometimes you'll be given it like this where you need to divide it out.
So I guess just to be clear, since you have the measuring point like this, because kind of like, you know, this shape here.
So that shape is representing the XLs.
Yeah.
The XLs, yes. And it is part of a bigger circle, but we cut it off because it's not physical beyond that because we have passive flows. Okay, so we're going to do some practice plotting these and then reading them off and that sort of thing, but that is how we get the ZL. So normally I wouldn't draw these lines on here like that. It makes it really messy. I would normally just go, all right, I kind of see the 1, I kind of see the 0.5, I kind of follow them down and I go right about there. And then you can make sure that that's right, you know, kind of follow the line up, follow the line over, make sure it looks good. This is our ZL. That's our first point. That's our load. That's what we want to get on here. Now we want to do the thing we talked about the last time. We want to draw a line. We want to draw a circle. Okay, so let's do those. The line starts from the center of the Smith chart. It's got to go through your point and go to the outside. Something like that's pretty good. We'll see. You want to do your best. I'm a little off, but it's not horrible. You can kind of see how close I am there. I'd say that's probably okay. Okay, now the question says, find the reflection coefficient, find the voltage standing wave ratio. Let's do the standing wave ratio first. Okay, let me double check that my circle is okay here, because sometimes it's not centered on here. Okay. That looks, oh. There. Need to make it a little bit smaller. There. Even a little smaller still. There. There. That's pretty good. Yep. So for me, it's really annoying because I just have to do it by trial and error. I just make sure it's a perfect circle. I adjust it until it has to be centered in the center of the Smith chart, and the line has to go through the ZL point. For you, it's easy if you got a compass, if you're doing it on paper, because you just put it in the middle, put the other side on the ZL point and go do your circle.
So you make your circle around the center point first.
Yep, it's got to be around the center point. Exactly. Yeah, yeah. Okay, let's do voltage standing wave ratio first. We'll do B before A just to get it out of the way. Can you tell me what it is just by what you've done so far? Sorry? Sorry? Oh, okay. So you're doing the gamma first? So no problem. Let's do gamma. So I had said voltage standing wave ratio. You were thinking voltage reflection coefficient, but let's do it. Let's do that then. Let's do A. No, so what you said, so I think you just calculated the magnitude of the reflection coefficient. So yeah, so let's avoid any confusion here. Let's do it in order. Let's do part A. Part A is the voltage reflection coefficient. Remember, the voltage reflection coefficient is the gamma. The standing wave ratio, we normally give that either an S or an S standing wave ratio, sometimes maybe with a V, okay? So the gamma is the reflection coefficient. To get that, you got some options. I'm gonna give you a minute to try to do it. This is the one that we measured and all that stuff the last time, okay? So I'm gonna give you a second. If you've already done this, then work on the voltage standing wave ratio. If you've already done that, then look at part C. How about this for those who are stuck? How do you do it just in words? How do you get the magnitude of the reflection coefficient? Sure, yeah. Yep, which one's on top? Which one's on the bottom? That's right. It should be less than 1, okay? So you measure this, you use your ruler and you measure that. It doesn't matter what units you're in, just be consistent. You measure that distance and then you divide it by the distance to the outer edge, but this edge here, because this is really the edge of the Smith chart. These are just scales at the end. This is really the edge of the Smith chart. That's option A. Option B is you could just measure the distance to the load. In other words, you could just measure that, call that like D1, and come down here and go that way, however far D1 takes you. That's the other option. So what are some values? Calculate yours and tell me what values you get for magnitude of gamma. .6-ish, okay, and I think you got 0.62, is that right? Yep. I can actually see what I can get here. Let me see what I get while you guys work on it. So you see, I'm using this line length because it's the radius of the inner circle. And then I can move it down here. So I get 0.62. Okay. 0.6 is a little borderline. I would just double check that everything is, I'd say, 0.61, 0.63, that'd be fine. 0.6, I would just double check that everything's in the right place. Yeah. Any questions on that one? Anybody get anything significantly different? So you can always just do this distance divided by that distance. Yeah. So distance from the center to your ZL, write that down. Like you get it in millimeters, centimeters, whatever. That's like D1. And then center to the outer edge, and anywhere is fine because it's all the same distance because this is the center of a circle. So any there, you write that down, same units, D2 say, divide D1 by D2, okay? All right, so I get about 0.62. No units or anything. Gamma doesn't have units. Gamma has a magnitude and it has an angle. So we need the angle of the reflection coefficient. So I want you to try to figure out what it is. I'll give you a second, look at it, see if you can come up with a number for what the angle of the reflection coefficient is. Okay, who wants to take a stab at it? 83, anybody else get something different? 83-ish? 82, any 82s? Okay, I'd say 82.5. So we know it's between 80 and 90. How do we know that? Because it says angle of reflection coefficient in degrees. It's the second scale from the inside out, okay? So that's why we look at where the line crosses that second scale from the inside. Immediately we know it's between 80 and 90. Then you have to go down to the increments. So 82, 84, all right. So around 83, I'm a hair less than 83. I'm just gonna say 83. It might be 82.8 or something like that, right, for mine, but I'm just gonna say 83 degrees. So you can read that directly off the scale. It's wherever the line goes through the line center, through your point to the outside, second scale from the inside, angle of the reflection coefficient in degrees. We've got gamma now. That's part A. Gamma is a magnitude and an angle. So gamma equals 0.62 angle 83 degrees. All right, any questions on that? I like this form for gamma. This is a good form for gamma. I like it. The reason I like it is because, well, let's just review what we're talking about here just for a second, because it's easy to get lost in this. We have a signal source. It's like your signal generator in the lab. It's spitting out a sinusoidal voltage, not unlike the voltage that would come out of your wall. Meaning the voltage goes up, it goes down, and it does it sinusoidally. It's got some frequency. In this example, we don't know what the frequency is. We weren't told what it is, right? But it's got some frequency, and it's in a realm where these transmission line effects that we've been talking about matter. It's connected to a transmission line. That wave doesn't travel to the end of the transmission line instantly. It can't go faster than the speed of light. It's an electromagnetic wave. The wave makes its way down the transmission line. It hits the load. Maybe it gets reflected. How do you know if it gets reflected or how much gets reflected? Depends on gamma. Gamma is the reflection coefficient. The amount that gets reflected is gamma times whatever was coming down. So immediately, if we knew the incident wave had a 1 volt amplitude, we know the reflected wave has a 0.62 volt amplitude going backwards. That's why it's nice to have it in that form. If it's in a real plus j times imaginary, it's not so obvious to me how much is immediately getting reflected. And there's a phase shift in the reflected wave of 83 degrees. Okay. We have a wave that's reflected. If it was perfectly matched and there was no reflection, gamma would equal 0. And where would ZL be on here? It'd be in the center, right in the center. PowerPoint prevents the screen from, when you're in presentation mode, it prevents the screen from turning off. And then I found that when the screen turns off, it stops sharing the content. Yep. Okay, so back to here. Center of the Smith chart is 50 ohms. Okay. So we've got a reflected wave. It's bouncing back. We have an incident wave at the same time as we have a reflected wave. They're going to interfere with each other. Some places on the transmission line, they're going to kind of add together constructively and create peaks. Other places on the transmission line, they're going to kind of cancel each other and create minimums. We have a standing wave on the line. Standing wave ratio is the voltage maximum divided by the voltage minimum. We are able to tell what that is from the Smith chart. So far from the Smith chart, we plotted on our ZL, and we were able to figure out what our reflection coefficient is. And part B is what is the standing wave ratio. So does anyone remember how to get that from the Smith chart? Yeah, it is right there where it crosses. The horizontal line across the middle of the Smith chart on the right-hand side, right there. So what do you get, and what would you read mine off as? Okay. Anybody else get anything different? So 4, 4.2, 4.4, 4.6, 4.85. So if you go all the way, then you know that your increment is correct, right? So this is 4.2, 4.3, or sorry, yeah, 4.2, 4.3 is like, yeah, about there. Yeah, maybe something like that. So I'm pretty close to 4.3. You get down to the point where the width of your line is kind of like, you know, on the order of the accuracy you're dealing with. So I would definitely say I am between 4.2 and 4.3, maybe a little closer to 4.3. I might just say, you know, 4.2. I think the actual answer, by the way, like if you calculated it, is 4.26. So you can kind of see how that is pretty close to maybe that, right? I would say 4.25 or something like that would probably be plenty. So S equals 4.25. Always, always, always standing wave ratio. As soon as you draw the circle, which is called the standing wave ratio circle, you just look at where it crosses. It could cross anywhere along here. As soon as you see it, boom, you know the standing wave ratio. No calculations, no anything. You just read the number off the Smith chart. That's A and B. So do we have any questions about A and B? All right, then let's step things up a little bit and do part C. The distances of the first voltage maximum and first voltage minimum from the load. I want to give you a few minutes to think about this, think about how to calculate it, and try to actually compute it, come up with some numbers for it. All right, before we can do anything, we have to know where the voltage maximum and the voltage minimum occur. Now, this really needs to be driven into your head. When you're in exams, there can be a little voice, my voice in the back of your head when you're doing Smith charts that says, if you're talking about distances from the load, you're talking about movement along a transmission line, you are stuck to the red circle. You can't go off of the red circle. If you are at the load, well, you can only go towards the source. You can't go towards the load if you're at the load. You're already at the load. Doesn't make sense. Look at the scale. This will always be on your Smith chart. Wavelengths toward the generator clockwise. Okay. So if you start here at the load, if you want to move anywhere, the only place you can move is towards the generator, which means clockwise, and you have to stick on the standing wave ratio line, on the red circle. Where is the location of the voltage maximum? Yes, it is the same point that we just talked about for the standing wave ratio. It's on the right-hand side. This is P max. Exactly, that is P min. Okay. Now we have to figure out how far do we have to go, like in wavelengths. Everything on the Smith chart is done in wavelengths. We have to figure out how far we have to go to get to, let's do the voltage maximum first. We have to get over here, but note that we're not coming there because we can't go there. That is the open circuit point on the Smith chart. We can't get there. We're not allowed to like go anything like that. We have to follow our circle. We have to get there. So we have to go from here to there. We use the wavelengths toward the generator scale. That's the outer one. We have to stop here. So we know our ending point. So if you look at the outer scale, the wavelengths of the generator scale, on the outside, it is 0.25. That is our ending point. Our starting point is where our line crosses the wavelengths to the generator scale. There's nothing magical about this number. It's just a relative measurement here. It's just a starting point. So what would you read line off as? Yeah, it's right in between 0.13 and 1.4, 0.135, and you can double check if you wanted to by doing the increments, but here it's really obvious. It's like really dead in the middle, right? So it's 0.135. Okay, so I want you to now calculate D max and D min. I'll give you a second. I'll give you a minute for that. All right, do we have a number for D max? What do you get for D max? Yeah, so it'd be 0.25 because that's our ending point minus our starting point, which is 135. So it's going to be, let's do it down here. All right. And what would D min be then? All right. 365. 365. Yep. So it'd be D max plus 0.25 lambda equals 0.365 lambda. So yes. Yep. 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 Okay. Let's say I wanted to make it a little more difficult on a midterm or something, and I said, I want you to find the distance to the third current maximum? The third from the load. So you're from the load, you got a current maximum, you keep going. Yeah, from the load, current maximum, current maximum, current maximum, that's the third one. Yes. So that was quick, that was good, I like it. Okay, so let's break that down a little bit. So number one, I said current maximum. That means voltage minimum. That means what we calculated as D min. So the distance to the first current maximum is 0.365 lambda. No, exactly. And so, exactly. So let's break that down again in case. So number one, it said current maximum. So you just think in your head, if it's current, it's the opposite one for voltage. So if I say current maximum, that means voltage minimum. Voltage minimum is V min. The first voltage minimum, which is the first current maximum, is 0.365 lambda away. That's the first one. But I said, what's the third one? It repeats itself every half a wavelength. So the second one is this plus 0.5. The third one is this plus another. The third one is plus another 0.5, which is plus 1. Okay. Any questions about that? Does that? Yes, that's what it would be. So just break it down into steps here. Current, opposite for voltage. Then think first one, then the next one's 0.5 away, the next one's 0.5 away. Okay. Okay. Well, we are done A, B, and C. And now we get to the fun one. D. We want the input impedance of the line. I'm going to give you a minute to think about this one. Like, what does that even mean? What might you do on the Smith chart? I'm going to leave this one for just a minute for you to think about it. Sorry? For the answer, I would slow down a little bit. You might be partially on the right track though. What does input impedance of the line even mean? Like, what are we asking here? Like, in terms of the question, what are we getting at? Before you hit the load? Before, like at the input of the transmission line, let me draw it here. So let's say we have a source. It has a source impedance. We connect up a transmission line right there. Boom, we got a long transmission line. Then we connect it up to this load, ZL. This transmission line is 3.3 wavelengths long. We want to find Z in, right at the input of the transmission line. Right before it, like right where we connect it up. So it takes into account the entire length of transmission line that has a load connected at the end of it. Okay. All right. So let's try to do that. So we're moving along our transmission line, right? So if we start at the load at our ZL point and we go wavelengths toward the generator. Sorry? Exactly. Exactly. And going back 3.3 lambda really means going toward the generator 3.3 lambda, which really means going around your circle 3.3 lambda. Now let me ask you a question. So let me pop over here. Okay, so let me ask you first, let's make this simpler. Let's say I told you that the length of the line wasn't 3.3 wavelengths, it was 0.5 wavelengths. What would the input impedance be? Remember 0.5 is a full rotation. Characteristic impedance? Load impedance. So remember, it's easy to get mixed up to think that 0.5 wavelengths is halfway around the Smith chart because it's literally got a 0.5 in it, but 0.5 wavelengths is a full way around the Smith chart. So if the question, which it doesn't say, but if it said the length of the line was 0.5 lambda, you'd start at the load, you have to travel on the transmission line around your circle, and 0.5 lambda takes you right back to where you started. So the answer would be your input impedance for that case would be it's ZL. Any integer multiple of 0.5 lambda, the transmission line doesn't affect the impedance at all. It's just kind of like transparent. You see right through it, right? Okay, so then I could say, what if I said the length of the line was 1 lambda? What would the input impedance be? 1.5, 2, 3, 3.3 though. We didn't get to 3.5, right? Exactly. So to do this, really break it down, we start here. We go wavelengths toward the generator, 0.5, 1, 1.5, 2, 2.5, 3. Now we have to go an additional 0.3. Okay. We have our starting point. Our starting point is still the 0.135 lambda. So what would our ending point be? 0.435. We have to add 0.3 lambda to it. So what we're really doing here is we are starting up here and we're coming around this way, 0.3 lambda, to end up at what did we start at? So 0.435, right there. Anybody want me to explain that again? Any confusion on that? One more time? Okay. The key thing to remember is a full rotation around the Smith chart is half a wavelength. From yes, wherever you start, if you rotate half a wavelength, you end up back where you started. So if we start at ZL and you went a half a wavelength away from ZL towards the source, towards the generator, you're stuck to your standing wave ratio circle, you'd end up exactly back where you started after 0.5. After 1, same thing. After 1.5, after 2, after 2.5, after 3, we are exactly where we started, right? But the line isn't 3 wavelengths long, it's 3.3. So we have to go an additional 0.3. Our starting point is 0.135. So our ending point is 0.135 plus 0.3. Okay, so we draw a line from the center to that point, the 0.435 point. Exactly. Input impedance, exactly. So right here is the in. So we're just going around the red circle, and every time we go 0.5, you end up back where you started. So you subtract integer multiples of 0.5. And we subtracted 6 of them, basically, because the first 6 0.5s, we ended up back where we started. We were at ZL, but we had to go an additional 0.3. So we took wherever we crossed the wavelengths through the generator scale, the 0.135 is our starting point, and we had that additional 0.3 to go. So we ended up at 0.435. So what we really did was we started here, we traveled along our line all the way down to there. But I mean, really, if you want to be precise about it, it really is 3.3 wavelengths. So we really did go around 6 times, and then this additional arc that I drew here in blue, right? But if you want to make it simple on yourself, you just go, I could say it was, 303.3 lambda. It would be the same thing, right? What if I had said it was 9.7 lambda? What would that be equivalent to? Yeah, 0.2. It's integer multiples of 0.5. So you would subtract all the 0.5s away until you're just left with the 0.2. In other words, you subtract 9.5 away and you're just left with 0.2. So now it becomes a question of reading this value off. So we want to read off, that looks like a 3, but it's a Z. Okay. Z in. We want to read the value of Z in from the chart. I want you to try to do this because definitely there might be a mistake. It's easy to make a mistake with these sorts of ones. So we want to try to read this one off on yours or on mine. You always want to start with the real. All right. Yeah. Yes. Yes. Center. Yes. Yep. That's the Z. Wherever it crosses your line, because you're stuck on this red line. So wherever it crosses, that's your Z in. Sorry? Zoom in on the Z in? Yeah. I was trying to do it so you could still see the axis. Yeah. Okay. Let me just. Yep. Okay. So we had one vote for a number. Does anybody think it's that or something different? Okay. Okay. This is the place where it's very easy to make a mistake. And it would be a mistake and you would lose a mark on this. So the question is who's right and who's wrong, right? So what did you say again? You said 0.23 or something? Oh, 293. Then you did it. Then I think you're right. What I had thought you said was 0.23, which is a common mistake. In fact, people in the other section made it because it's very tempting to follow up the red line. And if you followed up the red line from this point, you're at 0.2, 0.22, 0.24, around 0.23. That's wrong. Okay. When you're moving down the transmission line, you're moving around the red circle. We're not moving on the transmission line. We are trying to read the value, the real and imaginary parts off the Smith chart. This red line has nothing to do with that. Those are the gray and black circles. Remember, those are the ones that we use to plot the ZL to begin with. So those are the ones that we use to read off the impedance value. So what we really have to do is follow it up. Something like that. I might be a little off. If it were me, I would go 0.22, 0.24, 0.26, 0.28. I might say on mine 2.75 or something like that, 2.7, 0.28. That is the kind of neighborhood. You can see here that I'm not quite on the 0.28 line. I'm a little bit less. So yeah. No, you have to follow the the curve up. Because when you said draw a straight line, between which 2 points?
Well, generally, we see where you're, where they, where those two lines cross.
Yep. From there, going where?
Just straight up. It's like, well, yeah, it's gonna be screwed up with that guy.
Which guy? That one?
Yeah, I said parallel.
So straight up? We'll just forget about that. We got to follow the circle line. We got to follow the circle line. As long as you just follow like that one up, and then you could follow the next one up and go like, well, I'm a little bit closer to the higher one, right? So I'm a little closer to the 0.3, but I'm not quite to the 0.28. So, you know, something like that. I'd say 0.27 or 0.275, something like that for mine would be good. So for me, Z, oh, let me undo that. Z in equals 0.2, I'll say 7, plus or minus? Minus, because we are in the lower half of the Smith chart, so the imaginary part's going to be negative. Now, what value will we get for this one, would you say? So here's 0.4. This would be 0.42. So, you know, oh, that was a bad one. Ah, no, because well, it wouldn't be horrible. Oh, wait, it would be horrible. 0.43 would be over there. Because let me just clean this up a little bit. So this is 0.4, this is 0.42, that's 0.44. So 0.43 would be there. But that's not what we want. We're not doing the blue line. We are starting here and we are following the arc down like that.
Oh, good, great.
So basically, when you're reading a value off of here, forget any of the lines we put on the Smith chart. Your lines don't matter. If you're reading off the real and imaginary parts, it's the lines on the Smith chart that matter. Those are the real and imaginary parts. Okay. So you might say 0.4, I might say like 0.405 or something like that. It's less than 0.41, so I don't know, 0.405. No, that one's curved as well. It's kind of, it's straighter, but it's following the arc. It's following like that arc right there. Okay. So are we done? We have to go, we have to unnormalize it. It didn't ask for a normalized value. So we have to multiply it by 50. Okay. So what's that? I don't know. If someone can punch that in, that would be good. 50 times 0.27. Okay. $22.5? 20.25? And it would be in ohms. All right. So, any questions about that one? The parts that, were we okay up to the point where we read off the value of Z in? Okay, and then reading it off, you just have to think about, how did I plot the ZL to begin with? Because I need to follow that same procedure reading it off. Like, I have to make sure these are consistent with each other. And when we plotted Z in, or ZL, sorry, we had nothing on the Smith chart. There was no blue lines, there's no red circles, there's no red lines, there's nothing. We just relied on the circles and arcs on the Smith chart. We have one more part to go. We have done the input impedance of the line. We need to do the input admittance of the line. We talked about this at the beginning and I said it was easy, but then gave some ugly formulas for it. But then I said, it's on the opposite side, right? You just continue the line through. So we continue this line through because it's asking for the input admittance. We take the line that started from the input impedance and extend it through. If it had asked for the load admittance, then we would take this red line and extend it through. Okay, but it asked for the input admittance. Question?
Would it be a more habit to just draw two straight lines through to limit inaccuracy of redrawing on the second line?
Feel free to do it. Yep, no problem. It's up to you. It's not a bad idea to use colored pencils if you got them. Okay, so I want you to try to read off, either on mine or on yours, what should I call this value, do you think? Like, what would be a reasonable name that I'd give it at the point where they intersect? Sorry? Y in? Y in would be a good one. Y in. Y in. Just to keep straight what we're talking about. Input admittance. So try to read it off. Try to read, this is more practice on reading off these values. So for the real part, it's the circles you can see the whole circle of. For the imaginary part, it's these arcs that go like that. They go in. Those all go into the like right-hand side, and all of the real parts, you see the whole circle. All of the circles, all of the right-hand sides of them, they also kind of go in over here too, but they more like are tangential to the right-hand side. The blue one? Oh, so the blue one, we already had this half of it, right? Extended it all the way through. It's got to go through the ZN point, and it has to go through the center of the Smith chart, which I'm slightly off on, I can see. So let me adjust it a little bit. When you say quadrants, okay. All right. So Y in, we need a real part. What would you say the real part of Y in would be? Okay, 1.13. Anybody see anything different? 1.15. So what you got to do for the real part is you got to follow these circles. So you'd follow that down to here, right? So you could kind of follow these two and go, well, it's in between those two, right? And those two are 1.1, 1.2, right? Note they're not always like the same increments. So that's 1.1, 1.2, 1.3, 1.4. So it's in between 1.1 and 1.2. So it's pretty close to the center. I'd probably say 1.15, 1.15. Yes. Something like that. Nope, the x-axis. So in this example, like if you were in between like 1.1 and 1.2, I'd say that's probably a pretty reasonable margin of error, which really coming up here means you're like, you know, you could be kind of anywhere from there to there, that sort of thing. I'm going to be looking if you did the method correctly, not like, yeah. Yes, so there's definitely margin of error. Don't worry about that. Normally, it's not a problem. Normally, it's just you did the wrong thing if you lose marks. Yep. That was your question? Oh, okay. Oh, fair enough. Okay. Oh, okay. So we said 1.15. Is it plus or minus? Because we're in the upper half. And now we need to read off the value. Okay, so for these ones, we follow the, I'm pretty much right on that line, aren't I? So I follow that one up, 1.7. Yep. You're gonna be in the neighborhood though, right? So I'd say it goes up to there, so I'd say 1.7. Now, we're not done y in either. So how did we get how would we get a little y? Well, we would divide by y naught. So we have to multiply by y naught. Remember, y naught is just 1 over z naught, which is 1 over 50. So really, this is y in over 50. So we would take 1.15 divided by 50. And I think you get something like 0.02. And then plus j, and then you do 1.7 divided by 50 and it'd be like 0.034 or something like that. And it'd have units of scenes. And that is the total example. Question? No, you're good. Any questions? There must be some questions. We got like 2 or 3 minutes. I could go over again any of the parts of this. Sorry? Oh, good. I hope that it goes well if you see these on the midterm or the final, which is okay then. So I guess we can stop. Oh no, let me just do this. I'm just going to pop over here. I'm not going to get into the new material, but I just want to point out this is the last set of notes for part 1 of the course. It's impedance matching. It's our last topic. We are now done all of the content in quiz 6. And on Wednesday, quiz 7, our last quiz will be posted. And we are in section 211. So we're right near the end of this chapter of the book. All right. So we'll start here on Wednesday. There's not a lot of notes here. There's just a few things we're going to talk about. And then we're going to really dive right into an example, and it'll be example like the whole class, pretty much. Okay, so I will stop recording.